In this historical overview of pure mathematics, we will start in the year of 2000 BCE, which means before Common Era. The period of first 500 years shows important results of Babylonian mathematics, which includes the square root of 2 approximated to 3 sexagesimals. Nowadays, this would have been accurate in 3 decimal places, but the sexagesimal system was used at the time. It takes 60 as its base, and we still use it in our clocks. Babylonians also knew Pythagorean triplets, although this knowledge was predated by Egyptians. The long period of 500 years is here represented by a narrow strip, but these strips will gradually expand as we move through eras. As the progress becomes exponential, I try to keep up with it using a logarithmic timescale. What will be typical for next 2000 years is the use of rhetoric and geometry. Algebraic concepts are expressed geometrically and in full sentences, with no use of symbols other than for numbers. This is the time when Greek mathematics gave us its most important results: Miletus deduction, Pythagoreans the famous theorem, Euclid Elements, the most influential textbook in history, Eratosthenes' Ars Circumferens, and Apollonius' conic sections. Plato has argued that no other tool than a straight edge and a compass shall be used in geometry, and created a philosophical perspective called Platonism, an idea that the mathematical objects are ideal and independent on our world, a philosophical position that is relevant to this day. Elsewhere in mathematics, Aristotle established what for 2000 years appeared to be all that is there in logic and reasoning, and Archimedes remarkably worked with infinitesimals. In terms of algebra, we can argue that this period was a step back since the time of Babylonians. At first, square roots were guessed using pre-calculated tables. Pythagoreans knew a general procedure, but rejected the existence of irrational numbers. This, however, changed with Euclid. Things have finally turned for better around the year 250 CE, which means Common Era, when Diophantus wrote a collection of solved algebraic problems called Arithmetica. This also marks the start of a period of 1000 years known as the syncopated stage of algebra. Some symbols were introduced by Diophantus and later Brahmagupta, moving away from geometrical representations, but still, no symbols for mathematical operations were used. The life of Diophantus also coincides with the destruction of the great library in Alexandria, although as an institution it declined much earlier. Proclus, who lived in the 5th century CE, was the last Hellenistic mathematician. After him, not much happened in Europe. Elsewhere, however, Chinese astronomer Zhu Chongzi used Cavaliere's principle, Hindu mathematicians introduced decimal system with 0, and Persian polymath Musa al-Khwarizmi wrote algebra, establishing algebra as an independent discipline. This was also the point when balancing was added to equations. Later, a Jewish mathematician Abraham Barhia will have brought al-Khwarizmi's work to Europe as early Renaissance was just kicking off. Finally, it was Fibonacci who introduced Hindu-Arabic numeral counting system to Europe. While algebra steadily, if slowly, progressed, isolated discoveries were made in analysis. Bhaskar II had already used derivatives and Rolle's theorem 500 years before Newton and Leibniz were born, and functions were proposed by Sharaf al-Din al-Tusi. The first real symbolism perhaps appeared in the work of Ibn al-Marakshi, and to us a familiar symbol for addition appeared shortly afterwards, around 1360 CE. A singular influence had the work of Al-Khalasadi, although it is now considered more of a compilation of previously invented notation. As other symbols for mathematical operations started to appear while Renaissance was in full swing, things have started to happen fast. Girolamo Cardano published a procedure to solve cubic equations based on discoveries by Del Ferro and Tartaglia and recognized imaginary solutions. François Viète introduced much more than algebraic notation, and Napier invented logarithms. In geometry, Brunelleschi introduced geometrical perspective into painting, Bartholomeus wrote trigonometria, and Kepler formulated elliptic laws of planetary motions. While I was researching the chart, a single moment struck me as pivotal. It was the introduction of the coordinate system by Descartes in the mid of the 17th century CE. Yes, symbolism made overall progress possible, but there is no single invention that has influenced so much. Count that impossibility of doubling the cube would not have been otherwise possible to prove. Count that we would not have been able to visualize the complex brain from algebra, and count that functional analysis has only started afterwards. In my mind, I have no doubts that this was the single most important event in history of mathematics. Thank you, René Descartes. Immediately after this great innovation, projective geometry, which had a different setting to Euclidean geometry, was a major focus. Pierre de Fermat used coordinate geometry to revisit Diophantine equations and formulated his famous conjectures on the margin of Diophantine Arithmetica. Newton came up with first fast approximation of pi, while Jones came up with to us a familiar symbol for this important constant. The 18th century CE was a century when generality of algebra was used to prove theorems, which was a non-rigorous way of manipulating infinite expansions. It was also the century of a mathematical superstar, Leonhard Euler. Apart from solving the Basel problem, which brought him the fame, he proved E irrational and came up with the first theorem of topology, the polyhedron formula. At the beginning of the 19th century CE, mathematics was still about Euclidean geometry and real numbers, and used Aristotelian logic. By the end of the century, we had abstract structures. In geometry, non-Euclidean geometries were discovered, and Hilbert finally reworked the old axioms of Euclidean geometry, while previously popular projective geometry lost its appeal. In algebra, Galois theory was slowly understood, which meant an explanation why some polynomials can be and others cannot be solved in radicals, and we had proofs of transcendence of E and pi. In functional analysis, Cauchy rejected generality of algebra and together with Bolzano and Guderman made rigorous. Analysis, as we know now, was only born here. Finally, given Leibniz's algebraic logic was still forgotten, the first real additions to the Aristotelian logic were made: quantifiers, Boolean algebras, and Platonism gained its competitor in logicism. If there is one other moment in history of mathematics that in my eyes can compete with outreach of the introduction of the coordinate system, it is the foundation of the set theory by Cantor in the last quarter of the 19th century CE. Remarkable already in the aspect the whole field was founded by a single person, it ultimately resulted in concealment of even more abstract mathematical spaces, including the whole field of topological spaces. That, alongside of the attempted and provided foundations for mathematics, make it to me the second most influential event in history of pure mathematics. I would have thanked Georg Cantor for inventing the set theory, but then I think of all the headache and craziness it caused. The 20th century CE was started with Hilbert's program, an attempt to put mathematics on firm logical foundations, and its intuitionistic counterpart. Gödel's incompleteness theorems meant the end of the program's hopes, while the classical first-order logic remains a mathematician's tool of choice, pushing weaker intuitionism to the domain of computer science. If you share the preference for strong logical systems, it's reassuring that Lindström proved the first-order logic the strongest, satisfying compactness and Löwenheim's column property. Even with the help of logarithmic scale, the explosion of results in the 20th century makes the choice, including the charts, somewhat personal. Instead, I will end the video mentioning that the chart includes two great results that were ultimately proven, the last Fermat theorem and Poincaré's conjecture, and two that still stand, Riemann hypothesis and Hodge's conjecture. And here you have it, history of pure mathematics in one math chart. Best wishes from Math Charts!